Welcome back. My name is Adam Soroka, Managing Director for Cavendish Group. I'm delighted to be joined by Bryan Glover, CEO of Honeywell UOP. Thank you very much, Bryan, for joining us for the event. It's an absolute pleasure having you taking part in this. And also, I gather you're going to be also in the panel afterwards on sustainability. So welcome, first of all, to Future Downstream. Now, I want to ask you a few questions, focus very much on the sustainable issues we have within the sector. This event focuses on two parts: innovation and technology, and obviously decarbonisation, which are sort of key issues we're having with the downstream industry. First of all, what do you think are the challenges of developing and delivering on a successful, let's say, hydrogen economy?
Okay. Well, thank you, Adam. I appreciate the chance to be here. I'm really happy to be able to spend a few minutes with you today and participate in the panel after this. But, in thinking about hydrogen, I think there's a number of challenges, probably three primary challenges that everyone is facing when it comes to hydrogen. So one is, depending on the source of the hydrogen, it's either having the primary energy supply available. In the case of green hydrogen, having electricity available, but electricity available from a renewable source. In the case of hydrogen that comes from natural gas, so in the case of blue hydrogen, it's really having a mature capability and access to sequestration, long-term sequestration capacity. And then the last thing, of course, is cost. So looking at hydrogen for any purposes beyond chemical hydrogen, looking at it for energy purposes. In most cases, there's some upgrading cost because, whether it's green hydrogen or blue hydrogen, you're moving from a primary energy source, going through a transformation to create the hydrogen that's required in order to provide the additional energy. So both the cost of production of that hydrogen, but also the capital intensity of hydrogen production. So I think for blue hydrogen, maybe the bar is a little bit lower. For green hydrogen, I think there's a lot of innovation and development that's going to be required to really get especially the capital cost and the overall efficiency to a place where it becomes a little bit more viable option.
Well, it's a good point because following on from that, we had this mentioned. There's many different types of hydrogen, as you know. I think that the number of colours that were mentioned, even in our last event, were, don't know, maybe 30 or 40. Blue and green are probably the most common that were discussed today. In your opinion, what's sort of the difference, and how does each one get affected by the usage? Because what's better for short-term use, long-term use? What's the difference? How they're going to be applied? Because I think that's something which probably needs a bit of clarity in the marketplace. Is what is the future? We obviously need to use different types of hydrogen, but what do you see each one contributing in the next sort of few years?
Yeah, I think if we talk about blue and green, which I think are the two primary variants that we'll be looking at in the future, I do think it is distinctly different. The scenarios that support each one and support rapid growth of each one. If we look at blue hydrogen today, it's, I believe, a very viable option for hard to decarbonize segments, especially energy supply. But it works when a source of carbon sequestration is available. So in terms of geographically or geologically, it's really not going to be a solution for everyone. To be most viable, you need to be near a supply of natural gas, and you need to be near an opportunity for sequestration. And so I think that draws a bit of a boundary around the areas of the world that can most directly apply blue hydrogen. Now, one good thing about blue hydrogen is, especially if it's used for hard to decarbonize energy purposes for combustion, you're really stripping off essentially all the CO2 prior to combustion. So you can really quickly get decarbonized combustion. But that requires also that you're controlling fugitive emissions all the way back through the production chain of the natural gas, which remains one of the, I think one of the challenges for blue hydrogen is to make sure that, by the time we actually capture the CO2, that we've done our best to really decarbonize the chain all the way back, or at least, reduce the emissions perspective. But, I think in that regard, places that can support blue hydrogen, we see that actually growing quite quickly. Certainly there's some cost, but with modest governmental incentives or modest corporate subscription to the incremental costs, we think that can go very quickly. Green hydrogen, on the other hand, technology is deployable today. There's a number of evolving electrolyzer technologies that bring promise for even more efficient hydrogen production going forward. But a key challenge for green hydrogen is one, the cost of electrolyzers today, but two, the fact that it requires a decarbonized primary energy source. And I think maybe that's the longer term challenge, even more than the cost of deployment, is the fact that, for green hydrogen, what you want to avoid, what you need to avoid, is achieving a local optimum that's really not a global optimum. So, really requires renewable power and a significant decrease in carbon intensity of the general electricity market in a region or globally before green hydrogen really starts to provide a solution. Right? If the electricity generation requirements for green hydrogen mean that someplace we're burning more gas or coal, we're really not getting the decarbonization effect that we really want to for green hydrogen. So I think for green hydrogen, we certainly see this being an important element going forward of decarbonization, but one that maybe takes a little bit longer to develop because it does require significant growth of renewable primary energy sources in order to make sure that green hydrogen production truly is net reduction to greenhouse gas intensity.
It's a very good point, Brian. Moving on, obviously, because we haven't covered it a lot today, is on recycling technology. It's going to be referenced a little bit into the panel, and the circular economy. We talk about the circular economy. How can we how can it become efficient across the value chain? How can we get circularity more in the first part of the value chain? Because obviously we look at different parts of the value chain, but what about the first part of the value chain?
Yeah, I think circularity in the early stage of the value chain probably come from two primary areas: either circulation, circularity in carbon through renewable feedstocks, whether that's renewable plant-based feedstocks for fuels, plant-based feedstocks for polymers, having carbon circularity there in the case of renewable fuels, and maybe net carbon reduction in the case of biofeedstocks for plastics. I think that's one way to look at circularity. And then the other, I think, primary mechanism for circularity, at least in the downstream industry today, is direct circularity of the materials. So turning waste plastic back into feedstocks. Now, ultimately, maybe even more ideal if the original plastic came from a biosource, and then you could fully recycle it. But even fossil-based materials, as long as we can get those back into the feedstock chain and do it with an overall reduction in carbon intensity, then I think we're making progress. And so we see ultimately with the right sort of global approach to collection, and with full spectrum recyclability on plastics, everything from smart mechanical to smart chemical recycling, probably up to 90% of plastics that go into society today ultimately can be recycled, and ultimately can be recycled at a fraction of the carbon intensity of fresh polymers. Certainly it's not zero, so further abatements required beyond that. But we look at, for us, we have an upcycle technology, we call it, that's for recycle of harder to recycle plastics, things that naturally are not easily recycled through mechanical recycling. And with that, we can get significant reduction in intensity relative to fossil source virgin plastics.
Very good point. One last point, Brian. What's the, in line with the theme of the event, what do you think the refinery of the future looks like? What are the threats? What are the challenges that the downstream industry is facing, especially over the next few years? What do you think?
Yeah, I think the refinery of the future, or I've started thinking about it more a little bit, the refinery for the future. So a real
Yeah.
future leaning folks in the downstream industry are going to be looking to shift significantly to petrochemical production. Now, clearly, that's not a play for everyone. There's, in transition, there's a need for fuels as we go forward. But certainly being able to shift a refinery to heavy petrochemical production, thereby really reducing the scope 3 contribution of that refinery and maximizing the efficiency along the way, which for us is really, energy efficiency, energy intensity, but strong and careful molecule management. So there's, historically in refining, there's a lot of conversion involved. And I think we're finding smarter and smarter ways to achieve that conversion, where you selectively convert molecules that want to be, let's say, long-term in the petrochemical chain. Things that naturally want to be olefins, we want to convert them to olefins. Things that naturally want to be in the BTX chain, we want to be able to convert them into the BTX chain without using extra resources to try to convert them to something that they less naturally want to be. So I think refinery of the future, refining for the future, will involve heavy petrochemicals and really trying to minimize the number of processing steps to get to those petrochemicals, and as well minimize the amount of hydrogen that we deploy, because typically hydrogen is the tool we use in a refinery, one, to break down large molecules, but also to change the character, right? To change the hydrogen content and move back and forth between olefins, aromatics, or other types of chemicals. So use the hydrogen that's required in order to get the molecular weight reduction, but don't overuse hydrogen, because that creates a net economic and a net carbon footprint drag on what we're trying to achieve. So I think ultimately it's that, plus producing the fuels that we need, the cleanest fuels that we need for transition in the best way possible, and then bringing on a lot of renewable fuel production as well.
Fantastic, Brian. Brian, I really appreciate you coming on for this. So it's been invaluable for the event to get your opinion. So I really look forward to your contribution later on as well on the panel. But once again, thank you for joining us on this session.
Well, thank you, and thank you for inviting me. I've enjoyed being here so far, and I look forward to participating in the panel. So thank you.
Thanks a lot, Brian. Fantastic insights from Bryan Glover, CEO of Honeywell UOP. Really highly skilled and highly knowledgeable on the sort of the general industry. But I think some of the points he was making on the hydrogen economy, which is going to be discussed later, are really, really significant. So thanks a lot, Brian, for that.